Okay, we're ready to get started. For the next session, we've got Pedro Canahuati. I hope I've said that right.
Close enough.
Yeah. From Facebook. Following on from that, we've got lunch. So hopefully enjoy this talk.
I'll try to keep it brief so that everybody can actually get to lunch soon after this. As Josh said, my name is Pedro Canahuati. I work in infrastructure operations at Facebook. I'm going to talk a little bit about operating at scale. So there are going to be three main themes that I'm going to talk about, and things that you've actually heard in a lot of the presentations you've already had, and things that you'll probably hear about in the next 2 days. But primarily things that help us operate at our scale. One is defining a culture to build a strong team to run a site of our size, creating the right tools that help you keep those teams small, and applying both when it counts, when you actually have a disaster. And what do you do when that crisis actually strikes? So here's a quick history of the growth of the site, right? Like over the course of the last 6-7 years or so, as Facebook's user base has grown, so have the features of the site. And that growth has been really exponential. Most of you guys probably have joined Facebook in the last 4 or 5 years, I guess, at this point. And over the last 2 years, that pace of innovation has not decreased. In fact, it's been the inverse. As you see from that graph, it's like actually increased even more. So the job of the technical organization that we have is to build a framework that supports that pace of innovation. So to give you a little bit of context on what we deal with, I'll talk a little bit briefly about the site architecture. Now, every company has their own site architecture, and the challenges that they have and how they run their things are basically defined by how they actually build that architecture. Ultimately, they're driven by how that's built, but how quickly you can change things are dictated by that underlying foundation. At its core, Facebook's infrastructure is really actually fairly basic, and a lot of people are surprised at this, but everything is really exercised to its max, and that's why we actually want to keep things very simple. Every system is serving millions of requests per minute, constantly pushing data, but from a simple high-level view, we have a load balancer, we have the web server, we have services that, and ancillary services that store data, compute, reassemble or transform that data on the fly, and render at the web server level. In order for us to run things effectively, though, we strive to keep things as simple as possible. Complexity actually confuses humans. For all of us that we know, when you're looking at something and you just can't make sense out of it, you literally like step back and you can't do anything with it. So engineers in general love to build beautiful, shiny, cool things that are algorithmic. They go to the CS departments, they go to engineering teams, and they look at these things and they say, I want to make something really, really beautiful. But at scale, what we really want to do is we want to make things simple. Simple is actually much more easy to manage, and it's just beautiful for us, right? So our clusters are divided into 3 types, primarily front-end, back-end, and service clusters. Front-ends are really almost the same footprint. They're rubber stamps, like I showed you earlier. We have load balancers, web servers, caching servers, ancillary services like feed, search, and scribe. The back-end service clusters the back-end clusters are basically databases, most of where we store our persistent data. And the service clusters are ancillary services that just make the site better. So when someone actually asks me whether they should buy big and tall, or if they should go actually wide and short, there's never really a simple answer to that. Making that decision to scale horizontally or vertically is actually very difficult. There's never really one true way to do it. If you build the subsystems that allow you to deploy your software, your OS, your configurations quickly, then adding hardware is actually relatively simple. You know, all of us here are talking about configuration management, and that's really what we want to strive for, right? But there's always trade-offs that you have to make on that. When you buy a large number of commodity servers, that's generally less expensive than buying a large number of a small number of really beefy servers. And a smaller server failing actually affects a smaller portion of the overall service. But more hardware is harder to manage. All of us who are in the operations side understand that the more servers you have, the harder your job is going to be. So we've been doing this for a long time. Probably a lot of people here have been doing it for dozens of years. So I wanted to pass on a couple of lessons learned that we've learned at Facebook over the last 6 or 7 years, but also just things that I've learned over the course of my history. In general, in the infrastructure side, and the engineering and operations side, there's always a tendency to blame the infrastructure for failures. That may sometimes be the case, but generally you should always remember that new generations of hardware actually take a long time to roll out, right? Whenever we have a new CPU or you have a new SKU of systems, it's a lot harder to roll that out, and changing the physical or logical architecture takes a long time. It's sometimes effectively easier to actually fix problems in software. So make sure that when you're actually building architectures, expect failure, right? You should prepare and build for those failures, and when you're talking with the engineering teams and their operations teams and executive managements, always have that present in your mind. Expect failure to happen. It's not a question of if something is going to fail, it's really a matter of when something's going to fail. And so you can help mitigate some of those failures by rolling things out gradually, making sure that you can actually test ahead of time. You can still do that quickly, and you should strive to build your infrastructure to isolate your failure domain so that something that actually fails inside a certain portion of your clusters or your infrastructure doesn't actually affect the larger site or other portions of your infrastructure. Networks are going to fail, disks are going to fail, your pods or clusters independently are going to fail. You should try to actually strive to build those so that they actually operate relatively independently of each other. It's not always something that you can do, but it's something that you should strive to do. So fault tolerance is actually something that's also very difficult for a lot of people to get right. Once a service reaches sort of multi-thousand server capacity, failures are always going to be present. In our infrastructure, it's not a question of like, is something failing? I can always definitively answer that question with yes. There is something failing right now at this moment. You sometimes won't know what the impact of that failure will be, so you should consider shooting it in the head to test it, actually. There's a lot of companies that do that, and at Facebook we do the same. Some of the other big companies like Netflix and Amazon, they have certain ways to do it. We actually sort of like do trial runs, we do fire drills, we actually do controlled tests where we actually shut down certain portions of our infrastructure to see what other portions of it actually will fail. This actually may seem counterintuitive to a lot of people, because you don't know, but you don't know how something's going to fail until you actually try to kill it. So do that. That allows you and your engineering teams to build fault tolerance in your system. So in order to build a culture that can actually manage large systems at scale, you need to hire the right people, right? It's kind of obvious, and that really actually is easier said than done. So I'll spend a little bit of time talking about what we look for at people at Facebook. So over the last couple of years, everybody's been talking about the DevOps concept, right? Like, we're all here, we all know about it. This presentation is in the DevOps track. And the interesting thing is that I don't actually really agree too much with that term. Sometimes I actually hate it. The reason I actually hate it is because people seem to want to attach terms that they know to describe it. Some execs or fledgling IT guys read an article about it and start attaching known concepts to it. It's just, I don't know. They use these kinds of terms for it, and it's just not this. It's not a process. It's not the new ITIL. It's not something that you have to talk to your management about and put into your company. It's not something you're going to learn in a classroom. You should just really forget these terms. This is not working very well. So these are better concepts to actually describe when you talk to somebody about what DevOps is, or the awesomeness that is being an engineer who can actually code and knows something about what they're doing in the infrastructure side, on the code side, or on the system side. It's really a way of thinking. They need to think both ways. For the people who are new to this concept, when you talk to others and bring them into sort of like your secret society, you want to talk about the fact that there are people who there are people who actually write code, and there are people who know systems, but there are people who actually know how to do both, right? So the interesting thing for me is that when this concept actually started to be talked about, and people were saying that there should be people who do both, I actually thought to myself, doesn't really everybody do it this way? So these are things that you should actually be thinking about. So who do you actually hire? So anyone in this room who's actually in that hiring process knows that this is something that is really hard to get right. It's a lot more an art than it is a science. And at Facebook, we spend a significant amount of time discussing the people that we want to hire. Our interview process is rigorous, for sure, but it's not Machiavellian like a lot of companies that you've heard about, and I won't mention who those companies are. We interview for well-rounded individuals. We want people that know how to code. They need to know the nitty-gritty details of the TCP/IP stack. They need to know how an I/O subsystem actually works, and how the infrastructure is built. However, you could have all the technical merits of what you want in a person. They could pass all our interview tests, but if they don't have the right mindset, if they don't fit into the culture, you're probably still not going to get hired. So what you want to do is you basically want to hire engineers. If you have any influence in the hiring process at your company, start hiring full engineers, people who actually know both systems and know how to code. You want people who are going to be constantly learning from others, teaching others what they know, solving the problems regardless of whether it's their job or not, right? And actually, those people are generally going to code their way out of their problems. So one of the teams that I manage is named Application Operations, and the position there is actually, defining it is a bit hazy. It's not really easily defined. We want people who have sysadmin skills, they can write software, and they know a lot about hardware to understand how it's going to fail. Because we all know, like I said, it's not a question of if, it's a question of when. On our systems teams, we have people who, right now we have someone who's writing back-end software for provisioning systems on one day, and then literally the next day he's writing a device driver for an RFID reader that somebody's using at a conference that's happening today back in Palo Alto. Overall, we want to hire the best of the best, right? But you know that with the best of the best, just like with Mavericks, come some challenges, and those are challenges that are difficult to overcome sometimes. We have people who have crazy analytical skills that seem to get better under pressure. You throw some random things at them, they actually know what to do with it. They understand all the pieces of the infrastructure that fit together, and they understand when a failure happens, what to do about it. Those people actually need to stay focused on some really high, interesting leverage projects. Motivating these people is actually something that needs to be nurtured over time. It's not something that can just be left to their own devices. So an example of how we do that is when we bring people into the team and the company is we make sure that they're working on things that they want to work on. When people get hired, we find the skills that they have, what they're passionate about, what they want to learn, what projects that we have, and then we match them up with that. That's not something that every company really has the opportunity to do, but that's how we do it. Right? So throughout their career at Facebook, we can actually also move them around into different teams. It keeps them motivated, it keeps them engaged, it allows them to come up with newer, better ideas about other pieces of the infrastructure. So most of the teams that we actually build are pretty small, and this actually allows us to have a lot of really good impact in the problems that we solve. Because every team that we have and every part of the infrastructure that we have has really big problems to solve, a small team allows you to come up with really efficient ways of solving those problems. One person can have an amazing idea, and they'll go off and build that portion of the infrastructure. But overall, because the team is small, there's going to be a really close collaboration with a small set of people that keeps that sort of like that startup environment fresh. And a lot of us who've worked in a startup, that's what we really like. It's the jack of all trades that work on a lot of things, and they know a lot about every portion of the infrastructure. So this is a comparison of the operations and engineering teams at other companies that we know in life. This slide is actually about a year old, so the numbers are off. But John earlier from DTO was talking about the sysadmin to server ratio, and I can't actually share that information with you about what we have at Facebook, but I can be pretty sure to tell you that we pretty much blow out anybody out of the water. But at Facebook, on the operations and engineering side, based on our users to operations ratio, we have millions and millions of users that each operations engineer is actually responsible for. So that gives you a lot of really interesting motivations as well as ownership about what you're doing and the work that you're doing. But with smaller teams come a lot more constraints. You need to constantly prioritize. Some stuff just honestly is not going to get done. We talk about the concept of done is better than perfect at Facebook, and this is a hard concept to grasp for someone who's used to sort of like the typical ops world. Sometimes you need to ship something, you need to test it and iterate quickly, try it out. If it doesn't work, throw it away. And for anybody who's come from years ago, 10, 15 years ago in the systems administration world, that is a concept that's really difficult to understand. You really want something that's almost completely perfect before you actually put it into production. But honestly, it may not be perfect. If what you're doing solves a large percentage of the use cases, it's probably done. I mean, Luke was talking about that earlier in his presentation. Not that the stuff that Luke's putting out is not done. Perfect, sorry. Another concept that we talk about in building the culture is to move fast and break things. Again, this is one that could be at odds with a lot of your typical operations worlds. A lot of times when people see this, they actually shudder. It's really something that scares them. In a lot of companies, John I think was talking about this earlier, and so was Luke, your typical solutions for pushing things out into production are complicated, bureaucratic change management procedures. That just doesn't work for us. We have to do it differently. So we employ tools to actually get change management in place so that you don't have to have sort of the weekly meeting where somebody sits down and says, this is what we're going to put out into production. Do you sign off on it? Yes or no? Check this box, right? That's awful. Don't do that. We do it with things like hyper-increased communication. Everybody needs to know what's going on. That actually becomes difficult as well over time. The more people you have in a company, the more teams you have to understand what's going on. Your communication channels become pretty throttled, so you have to understand how to actually use those. Internally, we use products like IRC to keep the conversations flowing between the teams. We developed tools internally to centralize the information to understand change. This tool that's on the slide here is aptly named OpsFeed. It logs a ton of stuff from a myriad of sources and applications. It helps us correlate incidents with start and end times. Whenever somebody's rolling something out to production, we can actually go back and look at it and say, okay, this is when you actually did something. It actually allows us to quickly see who is responsible for that change in production. There's no red tape here. In this screenshot, it's actually 12 minutes at around 1 o'clock in the morning on, I think it was a Saturday or something like that. And this is actually about a year old. So now when you actually look at this feed, it's probably twice as dense, and there's probably 3 times as more changes that are going on. Now, there is a barrier to the system, is that you actually have to build an abstraction layer for everybody to be able to feed information into it. We want all the applications on our infrastructure and all the changes that are happening and all the manual scripts that people write to actually feed information into the system. And in order to do that, you have to make it simple. Make a simple API so the engineering teams can feed data into it. And by the way, you have to make it robust. It can't fail. If it starts to fail, then their systems fail, and they can't get their work done. We use internal groups. We eat our own dog food. We actually use our groups internally to communicate the stuff. We found that things for like upcoming launches or things that people need to know about in the company, it provides a really high signal-to-noise ratio of information that a targeted set of people should know. Not everybody needs to know, but if you join a group and you actually want to broadcast that information, then it's sort of a passive way of them getting that information. One of the highest leverage things that you can do to build the right team is to embed your knowledge into other teams, right? So share that information. And Luke was talking about earlier about the sort of like the 5,000 sysadmins that really know what they're doing, and they're trying to bring everybody else into the fold, into their society. This is something that everybody should be doing. Your typical operations and engineering environments that everybody talks about, or everybody's talked about before sort of like the DevOps concepts happened, is that there's a separate layer in between the operations and engineering side, and it's called QA. It keeps the build the business side separate from the run the business side. And we think that's wrong. At Facebook, we actually strive to remove those barriers. We sort of add a guardrail of operations around it so that everybody understands that you can work inside this guardrail and get your work done, and make the two teams work more closely together towards one unified goal. It's create an awesome infrastructure, keep the site up and running, and bridge the gap between operations and engineering. So how many of us have been in a sort of typical tug of war between the operations side and the engineering side, right? The engineer wants more servers so that they can actually get more stuff done. They're like, hey, throw more hardware at the problem, right? The operations side wants less. They're like, hey, it's difficult to manage. I can't manage that many systems. Your typical software engineer doesn't know and understand what it takes to deploy or run an application that they built. Your typical operations org is a black box to them. It's generally like, there's a bunch of these people who know how to make things run, and they keep the site stable, and I generally don't know about them until I call them because shit's broken, and they're the ones that actually bring it back up and running, right? So the engineering teams and just generally your technical organization should understand what it takes to do that. You should be talking to them all along the way. You should never be separate from them. They should know what it takes to do that stuff. Strong systems people who have a background in architecture and actually have been coding throughout their career know what it takes to build architectures at scale. This stuff isn't taught in school like your software algorithms that your typical engineer or software engineer knows. Ultimately, the engineering teams that build the systems that are responsible for it ultimately that build a system have the responsibility for their uptime. But that responsibility should be shared. It's not just the operations team to actually make sure that things are back up and running. Whatever engineer or team that builds it should help manage it. If a software engineer who's built the system is called repeatedly throughout the night, more than likely automation is going to be the outcome of those calls, right? Like you just continue to call them and tell them that something's broken and they have to help you to fix it. They're going to build something that's going to be better. What you want to do is you want to avoid ending up in a finger-pointing situation. Generally, this is where stuff really breaks down and companies start to crumble because of that. It usually happens because the teams aren't working closely together. You need to be involved early on in the design process. You need to be sitting next to them. Like John was saying, you have to have peers. Engineering and operations have to be peers in the design process and what you're doing. And if you do that, then you'll actually be in a much better environment. So, by the way, like the concepts that I'm talking about are not just synonymous with operations. This is synonymous with a technical organization. This is how you build a strong technical organization, software engineering operations. It's true of all engineers, and really it starts at the hiring process. So, as I was saying, the calls that end up in all that automation, right? That's how you run a large, complicated environment. You need to automate as much of the work as a human does as possible. When you're actually writing automation, make sure that you always think about what your mental model is for solving a problem and translate that into code. Humans are really bad at repetitive work. How many of us have just literally been like punching in the same command over and over again? And you know, in Lost, you had that guy that was punching in the same number over and over again until the island almost blew up, right? Humans forget. They need sleep. Or if they don't sleep at all, they make mistakes, right? Machines don't need hugs. They don't need feeding. They can do repetitive work over and over again until they fail themselves. Hardware's going to fail, so you have to build it to make sure that you understand when that hardware fails. But they're not going to be as bad as humans at doing repetitive tasks. So make sure that when you actually build that automation, build abstractions for that automation, right? Like Puppet, Chef, and configuration management today is actually helping us build those types of abstractions. Extensible libraries will actually breed bigger and badder tools. You know, if you can build knobs and levers to turn individual systems off, to shed load, to test things in production, or test smaller things in a smaller portion of your infrastructure, you're going to be so much better off and allow other people to actually use those tools and those libraries to build other systems. So here's a perfect example of a tool that we actually built, that we've been building over the course of like the last year and a half or so. There's an engineering blog post on our site that talks about what it actually is. It stands for Facebook Automated Remediation. What we noticed early on is that we spent way too much time SSHing into boxes and finding out what was actually running. We have services that I could be here for hours talking to you about each of the services that we have, and it's too many to enumerate, and a human can't keep that straight. So we built a set of daemons that uses a pluggable framework that allows engineering teams to write scripted responses to what to do when those things fail. It sends machines to repair, and the physical side of the house actually repairs those machines if they do it. It takes them out of production automatically so that we don't have to deal with them on the human side. If it actually can't do anything with the system, then it does escalate it to a human, and somebody has to look at it at that point. But this is an example of where a small team can actually have a really big impact. There were 2 engineers who were working on this problem. And it's now, we did some calculations, it's now doing the work of an example of what 200 sysadmins would be doing on our infrastructure. So, pretty cool stuff. Here's another example of a tool that we built called Cobalt. It used to take us approximately 3 or 4 people 2 weeks to actually provision the clusters, a set of, say, for example, 10,000 systems into our cluster to bring them up in line and actually serve web traffic. We built an abstracted library that allows us to build other tools on top of that. It's all written in Python. It brings up the 10,000 servers literally in about 10 minutes. So we've gone from a lot of people working on a problem to one script, somebody pushes a button, it's done. The interesting thing is that now we built other things on top of that, which is we can shift traffic from one cluster to another if there's a problem. We can actually turn the site off in mere minutes if we actually wanted to because of these libraries. It gives us it gives us new abilities to do things without having to log in into interfaces and actually click buttons and try and figure things out on the fly. So most of us have probably seen this kind of slide, right? It's your typical development to release environment. We're familiar with it. You ask somebody about it, this is their stock answer, right? Like you build something in development, it goes to QA, you test it in your staging environment, you deploy it out to production. But building this kind of environment actually can be costly. You have to be able to replicate the data into discrete environments. That can be expensive from an operational perspective, but also from a human perspective and a physical machine perspective. You have to keep those things in sync. You actually have to keep them separate. You have to make sure that things that are in development don't creep out into production and vice versa. There's a big overhead in managing this kind of stuff by hand. So at Facebook, we developed something that's called the Gatekeeper System. it's a way for us to try and minimize that environment so that we're not stuck in this cycle, vicious cycle of like testing and testing and testing before we put something out. We actually test a lot of things in production, and on the operation side, we use something very similar. It's not called Gatekeeper. We actually want to test things in a small portion of our infrastructure before we know whether it's going to be fully baked to push out to the rest of it. This is the basic functionality of the Gatekeeper system. It's not really rocket science. It's, if you want to try a new system out, try out this code. If you're not in that group that you can test it out, then try this old code. In actuality, it's actually more complicated than that because you can quickly build major nested dependencies in this system. But it allows you to do quick A/B testing and quick rollbacks as well. You can turn things off really, really quickly, which is an awesome thing for the operation side of the house. But at the same time, it also gives the users who are using the system a lot of power, and they can make a lot of mistakes, right? So you have to be careful about the way that you build that tool. So the way that we roll things out into production is fairly simple, or well-designed, as a couple other people have said before. We roll things out pretty quickly, and we do it in small chunks. We actually roll out changes to the infrastructure every day, multiple times a day. We do things in small increments. We start out with 1%, one server, a couple of servers, watch if things are going out well. If they're going out well, then we increase that to 10%. We do it in a couple of clusters. We do it in various data centers. We randomize that across the infrastructure. We build that up and go to 50%, and then we go to 100%. We're watching as we go, and as long as nothing's having major issues, then we continue to roll forward. If there is a major issue, or there is an issue that's ongoing and it's not something that requires us to roll back, we generally want to spend some time analyzing what's happening and actually roll forward. We'll have the engineers actually sitting there next to us, looking at the code, making changes, trying to recommit and then push it out to production, either on that day or very closely afterwards. There's actually a video out there from Chuck Rossi, who's our release engineering lead, and it's very interesting. You should read it, view it. Another one of our engineering teams is building a system called Tupperware, which is based on Linux containers. As many of you know, if a server is panicked, it's pretty much useless to us, right? So we're working with the team to make sure that they can allow us to algorithmically distribute servers in a heterogeneous environment, but also it's a way for us to able to communicate with it in the underlying software there without losing access to the server. So if the software on the server causes the machine to panic because it's using too much memory, then we actually have to reboot that server to get access to it. So what we did was we built an abstraction layer on top of it and said, if the server is using X amount of memory, then stop it. Kill the software that's on it, shoot it in the head, save the server. That's what we can actually use. Then we'll figure out what was causing the problem on the software. Ultimately here, the main positive takeaway is that we can actually manage the role a server plays rather than the server itself. And as everybody's been talking about, like configuration at code, well, this is a conference that we're talking about configuration management, so I couldn't get away without saying something about it, right? Make sure that you use your configuration management system to model your end state, not as an SCP on steroids, right? Like I've seen a lot of people implement just simple configuration management that's basically, it says, I have this copy of something that I have in my development environment, and I just want to push it out to production. That's actually not the right approach. Make sure that you shape your end configuration from your system to not have n number of config files with one individual change. Make sure that you're actually building a model and that you can actually apply that configuration to multiple diverse sets of systems. Avoid complex installation scripts after imaging. A lot of people end up doing a lot of stuff in post scripts, and it requires a lot of forethought, and you have to spend a lot of time trying to figure out how individual systems are going to use that script. Avoid that if you can. Save that for config management or application management. Where you can, build your system so others can contribute to that so that you're not the only ones actually managing that system. The last thing you want to do is to have a bunch of engineers who want to apply configuration management to your systems in production and have them all have to come to you to say, how do I do this in production? And then it just requires you to have to manage 600-700 engineers at the same time. That's way too much for one person to do. Lastly, we use code review for everything that we do in configuration management, right? If you're not doing that today, go back and start doing that. We use an open source product called Fabricator that we developed in-house. Anybody can use it today. We apply hooks into our configuration management system so that everything is code reviewed. Everything has a peer review. There's also another one out there that's pretty popular called Review Board. So if you're trying to figure out which one to use one of these two systems. So running a large network also means that you have to monitor it, right? So you can't just have all these systems out there with really cool tools and really cool software without actually understanding what's happening in the background. So the best advice that I can give you is really instrument the world. Do it early, do it often. Use that data to analyze trends over time. It's going to give you insight into how you're going to plan for the future. Build the system so that it's as real time as possible. Use open source software to do that, right? Like you can get things from Gangly, you can get Nagios, Munion, et cetera, et cetera. All those things give you insight into your monitoring of your infrastructure. Make it consumable by everyone in the company. That's one thing that I've seen a lot of people do, where they build the little system on the side that really only the operations side of the house understands how to consume that data or understand what it's really telling them what's happening. I think that's wrong. I think that you should actually, everybody in the company should understand what's going on the infrastructure at any given time. So for example, we have a system that we call Domino Hear that gives us insight into server-side errors on the infrastructure. It monitors in almost a real-time manner through sampling what's causing the most amount of problems. We divide it up into types of services that we're hosting so we can actually see which application is having the most amount of problems. This is open for everybody in the company to see. At any given time, if somebody wants to see what the health of the site is doing or what the health of their current service is, they can go to this interface and they can see, we're causing this many errors on the infrastructure. This is the portion of the infrastructure that's causing that error. And if it's an engineering team that's responsible for it, they can actually start going to fix it without anybody having to tell them that there's a problem. It's a consumable interface that allows them to do that. Another system that we built is called ODS, which is an operational data store. It's, like John was saying, that there's a lot of companies out there that do number crunching. We live and die by the number crunching. We need to understand what's going on with trends over time. We need to be able to transform that data into complex ways. All application owners can submit data into this system, and we want them to submit data into the system because then that gives us the ability to actually tell them when we see that graph go down, we can actually understand from an external perspective what actually just happened. There's an open source similar one to this. It's not exactly like this. It's called OpenTSDB. It's just a simple time series database that you can apply arbitrary data to, and then you can just read it in the back. If you don't have this in your environment today, think about putting something into play with this. Again, you have to build an abstraction layer that allows any team who's building an application to actually submit data to this. We have network analysis tools that allow you to see similar trends. It stores and graphs NetFlow data from our switches and our infrastructure, breaks it down by source port, and gives us the amount of traffic each of those services in the network is consuming. Oh, that's weird. So the problem, though, when you have a lot of these types of systems is that you have a data aggregation problem. You need to figure out what to do with all the inputs that you're getting from all this information. So we build our own system to do that, especially on the alarming side, right? So on the alarming side, we have a system that allows you to group levels of problems and slice them in various ways. For example, you can group them by criticality. We can group it by one specific type of alarm. We can do that by cluster. We can look at one specific alarm and say which are the clusters that are having that type of alarm. We can actually even group it by racks inside that cluster, and we can say which systems are having that problem inside that cluster. So my point as I was talking about all these cool tools that we've built is not just to talk about the cool tools that we built, but to implore you to work together with your engineering teams to build tools and to build your own tools that are going to ultimately drive your human decisions. The tools should actually help, should check for human errors along the way, and people should be disciplined about using those tools. The tools should enforce checks and balances so that you don't have to build bureaucratic processes. Your code reviews are a must, right? If you're not using it today, make sure that you're doing it. I'll say it again, right? If you don't have a peer review, it shouldn't go live, period. Your tools should help you decide if things should continue, stop, or roll back, and they should be able to minimize any off-the-cuff sort of on-the-fly changes. Okay, so now you've got this really cool team assembled. You have all these tools that you've built that are at your disposal. What do you do when that what the fuck moment happens, right? The culture you define and build and the technology you create helps you when that moment happens. And trust me, it's gonna happen, right? In every company I've been in, it really happens. So what do? At Facebook, when we have big problems, we call them SEVs, or severe events. So first and foremost, focus on fixing the problem, right? Everybody, when there's a really big event, they start complaining about like, if this team would have done this better, if you guys would have been able to figure this out before, if you'd known that this problem was happening earlier, like this would have prevented the problem. That's the wrong thing to actually focus on. Mobilize the right people, get the right people together, make the right calls. Everything and everyone should be focused on minimizing the impact to your users. Dealing with a crisis is something you need to discuss in the hiring process. We actually do this in our interview process. It's a question that we ask everybody is, what do you do when a crisis happens? What crisis have you been involved in? What crisis have you caused? It allows us to really understand whether they have the mentality to actually deal with this kind of environment. The infrastructure team actually has this slogan on a t-shirt. And I kid you not, it's not just a slogan for when a disaster happens, but it's an everyday thought that we want everybody on the infrastructure to think about. We want people focused on fixing things. So we actually separate the roles of who's going to be fixing the problem from those who are going to be making the decisions and communicating what's happening. In a complex environment, those can't always be the same people. You want the people who understand what's going on and how to fix the problem, fixing the problem. During really big incidents, the decision-making is not necessarily a democratic process. You actually have to have somebody who's sort of like anointed as a leader to basically say, we're going to go down that path, we're going to do this. They may make the wrong decisions, but at least there's somebody who's actually making, having order within that chaos. If you're really prepared and you actually think about these things ahead of time, you rehearse things. You build tools that allow you to get this right. You actually do fire drills and say, okay, let's shut things off and see what would happen, see how we react to these problems. Now that you've got everybody focused on fixing the problem, communicate what you're doing, right? Tell everyone that you're actually fixing that problem. Tell everyone that there is a problem. This is something that is really difficult to get right. It's also something that's often missed in a lot of companies. It's hard to balance the over-communication with noise, right? A lot of people need to know what's going on, but some people actually don't need to know. But at the same time, there are other people who are non-technical people in your organization that do need to know that there's a problem. They may be getting calls from their customers. They may be getting calls from, outside sites like TechCrunch or something like that. So they need to know that if there is a problem or if there isn't a problem. We communicate over IRC. We do things over email. We even do internal headers in our tools that let people know that there's a big incident. Remember those tools that I told you that allow people to make change and go out into production really quickly? Well, they need to know when they should not be using those tools. We've actually written something else, which is sort of like a master lock that allows us to lock everybody out from making any change into production. And there are only a few people who have the key to turn out that master lock off. So from a high-level perspective, this is effectively how we run incidents at Facebook, right? Like, figure out what's going on, tell everyone what you think it is, fix it, tell everyone that you think you fixed it or that you actually did fix it, then go back and review what happened. Do that, review after the fact. Don't try and do it on the fly. Actually, just fix the problem first, then you go back and talk about it. So during the SES, fall back on the tools that you built. Fall back on the things that you built during monitoring that allow you to get things out into production really quickly. Build new tools that are specifically for incident management if you do have a lot of incidents that happen on your infrastructure. We do, by the way. So, and then after that, once your event is over and you've got some time to breathe, review it. Review it with everybody, right? Do the postmortem that you have to have. You should always strive never to repeat the same mistakes and fix the problems in your code that you found caused the problem, or add them to your roadmap so you can actually do that later on. But the postmortem process really should not be a blame game. A lot of companies and a lot of teams fall into this problem here, is that they say, again, you should have done this, you should have done that, we should have understood this, why did you make that change, why weren't you thinking about this, et cetera, et cetera. Really fight back that tendency. Fight back with every ounce of your energy. Don't do that. Because what's going to happen is that if you do that and the people who are showing up to this review are getting blamed or attacked, you're not going to get honest participation in the future. They're not going to want to actually help you out in the future. So let's review what I've talked about, right? The best people make the best teams. Yeah, okay, whatever, right? Build tools that give you insight into what's going on into your system. Automate your way out of repetitive tasks. And when the shit hits the fan, take a breath, fix it, review afterwards so you can do it again. Rinse and repeat the whole process as the years go by. And again, remember, the concepts that I'm talking about are not synonymous with just operations. They're synonymous with a technical organization. This is how you build a team that actually can operate at scale. Engineering, operations, everybody in your team. And it starts with who you hire. That's about it for me. Any questions? I'm sorry, I can't hear you.
Why don't we use Puppet?
So we don't use Puppet, mostly because we have old infrastructure that was built on CF Engine. We're actually in the process right now of changing that from CF Engine to something else. We're doing a sort of head-to-head between Puppet and Chef. We'll probably announce which one we use when we actually decide. For the teams that are building software, we do. Most of the teams are building software, so we actually do that. On the engineering side, every team actually does things the way that they want to do it. Some of them actually use that process, some of them don't. It really depends on what problem they're trying to solve. Yeah, so again, the teams that are building the software that I talked about, we do it that way. Yeah. Wherever we can and things aren't built that are very specific to the Facebook way, to the Facebook environment, we do. We're going to try to do that, right? We have a couple of tools that are right now in the process of doing that. But like I said, we do have small teams. So when we try to build them, we do think about whether we can open source this tool in the future. But we're focused on trying to get the infrastructure as reliable as possible. And then we have a team that's separate, that's focusing on can we take this tool and actually open source it. We do want to do that, right? Like we do a lot of that. If you go to facebook.com/open source, you'll see a lot of the tools that actually do that today. Like I said, our code review is some of that. On the operations side, we haven't been as good about doing that, but we're going to start doing that much more. Yeah. Yeah. Yep.
So in one of your slides, you removed QA.
Yeah.
Assuming you still have people whose title is more or less QA.
Nope.
How do they fit into the new technical organization that you described?
Yeah, we don't have QA. And we actually don't have anybody who has a title QA. So the engineers who are writing the software are effectively the QA, Q&A team. But we also automate QA through a lot of things. Like we built an in-house tool. I think it's based on Selenium or something like that. Basically, that runs through a lot of the tests that would actually happen in production. Make sure that the browser can actually see what it's supposed to see. We have a lot of unit tests that happen before the test is rolled out to production. There's a lot of push blocking tests that happen. So when we're in the process of compiling the code that's going to go out to production, if any of those tests fail, nothing gets out there, right? So and we assign each of those tests have an owner. So if that test fails, the owner gets involved and actually looks at why it was causing that problem. So no, we don't have QA. Yep. Yep. Absolutely, yeah. So it does happen sometimes. Our system that's actually feeding that information, the system that takes the data, can sometimes fail. What we tend to do is we make sure that when the abstraction layer that we built is that if it can't submit that data, it queues it locally. We use Scribe to queue that data locally, and so that you can actually slurp it in later. For the operations side of the house, when that system is down, it's very critical for us to get it back up and running. That's the only way that we understand. It's not the only way, but it's one of the basic ways that we understand how the site is operating at the time. So we need to understand when it's down, we need to bring it back up quickly. If that system is down, we have all hands on deck trying to bring it back up and running. Sure. Users that get errors on the site. That's what keeps me up at night. Making sure that the infrastructure has enough capacity to be able to handle the influx of problems. So generally when we when we roll out a new product onto the site or a new feature, if it's something that's new that we've never had before, say for example photos and videos, we generally become the biggest of that on the internet. And I'm trying to gloat here. It's just because we have a very engaged user base. We have a lot of users on the site, and so they tend to gravitate towards that feature really, really quickly. So what keeps me up at night is making sure that we can actually build that, roll it out quickly. But also, if it starts to have a really bad impact on the infrastructure, that we can roll it back or we can turn it off. So we don't want users to have a really bad experience on the site. We don't want the infrastructure to fail because of one new system that's coming up. So that's the stuff that keeps me up at night. That plus hiring more people. Yeah.
So you all these various free features and all this great information coming in. How do your individual developers manage the signal-to-noise ratio? It's just an immense amount of data coming in.
Yeah, so data visualization is a really big problem, right? We have a lot of people who work on that all the time. Each team tends to solve it a little bit differently than the other. We try to build a system that gives people insight into it and solve 85% of their use cases. But then a lot of teams end up writing other tools, like Domino is something that we wrote. We have some other tools that I didn't talk about there that actually solve that problem as well. Yeah, but it is a difficult problem to solve.
You mentioned the many configuration files with just one change in them.
Yep.
I didn't quite catch that.
Yeah, so that's actually sort of like a slight into one, how we implemented CF Engine, and also a drawback of the way that CF Engine does things. Our SIS Control File is one of the ones that we literally, for every tier on the site, maybe one person wants to change one little configuration in it and wants to do sort of one change on it. And instead of us building a model that allows us to say, if you're this tier and you want this changed, we literally copy a new file with that one system, with that one change into it. I'm slightly embarrassed to actually say that we do that, but it's just, you should never do that, honestly. So, yeah. Over there.
Just getting back to the communication model, what are the criteria, what are the processes that you decide whether that communication remains internal to your organization or what's bad enough to actually have to release?
Primarily the impact to the users on the site and who's being impacted by it. If it's an internal application or an internal infrastructure component that's not affecting a large percentage of our users or the site, we don't broadcast that out too broadly. If it's just something that it's a tool that's broken that only a certain number of people on in the team are using, then we tell them that it's happening. Yeah, that's generally how that was defined. Yep. Both. So the Gatekeeper system allows us to roll out code and then turn it on once it's out in production. But the way we roll it out is also we roll out a different set of code onto the systems itself. So at any given time in our infrastructure, a certain set of servers has one version of the code, and another set of servers has another version of the code. And we try to roll that out and minimize the code that's out there on the different servers. Yeah. So that's something that the engineering team spends a lot of time making sure that there's always backward compatibility. We roll out code really quickly. We don't have a very long iterative process of making sure that we ship out code and then 2 weeks later we wait for the next version of it. It's literally every day, right? So it's a lot less work for the engineering teams to keep that backwards compatibility rolling. So generally what happens is that the code that's rolling out, if it's a new feature on the site, then we control it through Gatekeeper. We make sure that the code is out there first, then we turn it on through Gatekeeper. If it's new stuff that can't be controlled through Gatekeeper, generally users will, for a small percentage of time, they might get a different experience based on the server that they hit or the cluster that they hit, but it's not a big problem. Yeah.
Do you have to deal with security auditors, internal, external, and how does that affect operations workflow?
Yeah, sure. So every company has to deal with that, right, at some point or another. So it's an interesting dynamic there because you do have to make sure that what you're doing follows some compliance at some point. What we strive to do is make sure that we don't build some bureaucratic process, right? I can't tell you the actual specifics about how we deal with it, but if you can build something that actually satisfies the logging portion of it, the access controls, and the auditor's portion of it, then you're generally fine, right? That's what you have to do for compliance sakes. So when we build something that has automation involved in it, are there only a certain people who can actually make that change? Are there only a certain people who can actually push that change? Does it go through some level of peer review that allows you to get that audit portion of it? And is that peer review logged, right? So those are the things that actually get you compliant. So that's what we do.
I have a question about when you're rolling out YAML or test changes to segment the fleet. Is that a static segment of boxes, or is that a randomly selected portion of your fleet?
For a certain portion, it's static in the beginning so that we can actually watch, so we can understand the A/B before and after, and then it's a randomly selected set. How am I doing on time? Great. All right. Thanks, guys.